In the previous lectures, we discussed uniform and accelerated motion in the context of motion along a straight line. We now extend the discussion to motion along circular track. Consider the following scenario. A car is moving at constant speed v along a circular track having radius r. The position of the car after t seconds has passed can be described in a number of ways. The first way is to use the angular displacement, denoted by theta. The SI unit of theta or any angle in general is radian, and pi radian or 3.14 radian is equal to 180 degrees. So if theta is 1/4 radian, the car has moved 45 degrees. If theta is 1/2 radian, the car has moved 90 degrees. If theta is 2 pi or 6.28 radian, the car has just completed one round of the circular track, and so on. Angular displacement, like displacement, is a vector quantity. The magnitude is given by the numerical value of the angle itself, and the direction is given by clockwise or anti-clockwise as seen from the top. In our case, all the directions are clockwise. Another way to describe the position of the car is through the distance the car has moved along the track. The distance is obviously proportional to the angular displacement as you would imagine. In fact, the radius of the circular track serves as the proportionality constant. That is to say, this distance is given by the angular displacement theta multiplied by radius r. So if theta just now is 1/4 radian, that means the car has traveled by 1/4 pi times r along the track. If it is 1/2 radian, the car has traveled 1/4 of the circumference of the track. And if it is 2 pi radian, the car has completed a full round of the track or 2 pi r. Okay, a couple of things to note. First, after 2 pi radian, the car is back to its initial position. The car is back to its initial position again after 4 pi radian, 6 pi radian, and so on. Circular motion is a periodic motion. Second, notice I use the term angular displacement and distance. Please don't mistaken the two. We are able to compute the distance the car has traveled along the circular track from its angular displacement. If you recall our discussion of displacement versus distance at the beginning of this lecture series, displacements are given by these green arrows, connecting the final and initial position of the car. Distance, however, is given by the arc length along the circumference of the track, as indicated by the blue dashed line. After the car completes 2 pi radian or one full circle, the displacement of the car is 0 because its final initial position are the same. No displacement, but the distance the car has traversed is not 0. It is 2 pi r or the circumference of the track. Last but not least, although angular displacement has a unit of radian, it does not carry any dimension. The implication is that when you multiply the angular displacement to radius to give you distance, the SI unit of distance will be the same as the SI unit of radius, which is meter. And it does not become radian meter. If the radius is given in kilometer, then distance will also be in kilometer as well. We press on. Just now I mentioned that the car has been moving for t seconds. Assuming the car is continuously moving at constant speed, that's the assumption. Can we compute the speed of the car? Yes, we can. We have learned how to do that. Speed is distance over time. Hence, it is theta r over t. Take note that it is perfectly sensible to assume the car moves at constant speed, but it is impossible to assume the car to move at constant velocity, because by the virtue of circular motion, the direction where the car is moving will have to change constantly as indicated by the red arrow. The magnitude of this velocity factor, i.e. the speed, can be constant. As you can see, the length of the red arrows are the same, but their direction have to be different. Hence, the velocity factor will never be uniform. We will come back to this issue at the end of this video. Now, I would like to introduce a new quantity called angular speed. If speed is defined as distance over time, then angular speed, denoted by Greek letter omega, is defined as angular distance over time. That is theta over t. With this new quantity in mind, we can rewrite the equation to compute the speed of the car in terms of omega. V is equal to omega times r. The SI unit of angular speed is radian per second. Strictly speaking, since angle carries no dimension, we can also assign 1 per second as the SI unit of angular speed. But for a reason which will be made clear soon, we stick to radian per second. Technically speaking, we can also define the so-called angular velocity. By the feature of its name, angular velocity is a vector quantity whose magnitude is given by angular speed and its direction is given by clockwise or anti-clockwise movement of the car as seen from the top. By convention, positive angular velocity implies anti-clockwise movement. Vice versa, negative angular velocity implies clockwise movement. Hence, in our case, this diagram illustrates negative angular velocity. Moving on. I discussed just now that every 2 pi, 4 pi, 6 pi, and so on, the car periodically goes back to its initial position after completing the track. Capital T is used to denote the time period required to complete a full circle. The keyword is full circle. The term period in circular motion is only used to refer to the time taken to complete a full circle. Hence, still assuming the car to move at constant speed v, this period can then be computed as the circumference of the track, which is 2 pi r divided by the speed of the car. Or, in terms of angular speed, it is 2 pi over omega. The SI unit of period is of course the same as the SI unit of time, which is second. When talking about period, it is almost by default that we should also talk about frequency. Frequency, denoted by small case f, is defined as the number of circles completed in 1 second. The keyword lies on 1 second. Now, if you think about it carefully, frequency is the inverse of period. Think of this for instance. Let's say it takes 1 minute for the car to complete 1 round. That means the period of the car is 1 minute or 60 seconds. What about the frequency of the car? In other words, how many rounds does the car complete within a second? If it takes 60 seconds for the car to complete 1 round, within a second, the car will only complete 1 over 60 of a full round. It is the inverse of period. Frequency is always the inverse of its corresponding period. Since the SI unit of period is second, the SI unit of frequency is then 1 per second, which is strictly speaking is the same as the SI unit of angular speed. That is the reason why, to distinguish the two, we prefer to assign radian per second as the unit of angular speed and simply 1 per second as the unit of frequency. Sometimes in literature, omega or angular speed is also called angular frequency. If you stumble on questions in the textbook which ask you to compute angular frequency, that text wants you to compute angular speed actually. 1 per second sounds like a mouthful. There is a short form for 1 per second called hertz, which is the SI unit of frequency in general. So you have probably heard hertz being mentioned when referring to a particular radio frequency. We come now to the most intriguing section of this lecture. We established earlier that although the speed of the car remains constant, its velocity will never be constant because the direction where the car is heading is always changing as shown by the red arrows. This direction is always tangential to the track. At the same time, we also learned in Lecture 4.2 that change in velocity implies acceleration. Indeed, while performing circular motion, the car undergoes acceleration, a kind of acceleration which does not change the speed of the car, but only its direction. Such acceleration goes by the name centripetal acceleration. How do we visualize centripetal acceleration? Well, by definition, acceleration is the difference in velocity over time. Since time is a scalar quantity which does not carry any direction, the direction of the acceleration factor is given by the direction of a factor difference between the final and initial velocity, as shown by the purple arrow in this animation. Notice that this factor difference starts from the head of initial velocity factor to the head of final velocity factor. As much as possible, I try to draw the images in scale. The two red arrows, which indicate the initial and final velocity respectively, share the same length, meaning that the initial speed is the same as the final speed, but pointing at different direction. The two red arrows then form an isosceles triangle, or a triangle that has two sides of equal length, with the difference in velocity, or delta v, as its basis. Not only that, the two red velocity factors will also form the same angle as the angular displacement, which implies that the triangle with the two velocity factors and change in velocity factor forms is similar to this triangle, formed by the two radii and displacement of the car. Two triangles are called similar if they both have the same angles, which these two triangles obviously do. If you are in doubt, I guess your doubt lies with my earlier statement that the two velocity factors form the same angle as the angular displacement. Is it always the case no matter how large the angular displacement is? Well, yes it is. You can use geometry to prove it, but one easier or rather hand-waving way to convince yourself is via trial cases. For example, if the car has traveled for 90 degrees, which is a quarter of the circumference, the final and initial velocity vector will also be perpendicular to each other. If you don't get what I just said, please rewind this video until you get it. These so-called geometrical properties will be useful in deriving the equation for centripetal acceleration. First of all, because they are similar triangles, the ratio of their sides will be equal. Do note that it is the ratio of the sides which are equal, not the absolute length of the side itself. In other words, delta d over radius from the left triangle is equal to delta v over v from the right triangle, and hence we can express delta v as delta d over radius times speed. This relation is crucial since acceleration is defined as delta v over time, and we can substitute delta v with the earlier expression to give us the square of velocity over radius. The last step is obtained after converting delta d over t to v, in accordance to the definition of velocity. How about the direction of centripetal acceleration? Well, the direction of centripetal acceleration should be the same as the direction of change in velocity. Hence, as illustrated by this animation, the change in velocity, i.e. the centripetal acceleration, is pointing radially inward into the center of the circular track. In conclusion, centripetal acceleration is equal to velocity squared over radius, and it is always pointing radially inward toward the center of the track. This is another important fact we should keep in mind and heart throughout this course.